configuration where.
Sorry, Shimeng, I forgot to start earlier, but please go ahead.
Okay, I will keep going. Okay.
Yeah.
So then the channel conductance can be modulated by the threshold voltage of this gate stack. Therefore, we can implement the multi-bit weight as well. So given so many implementations, possibly at the device level, we need to have some early design stage exploration. So here we show some examples of the device level innovations on the R-RAM exchange memory of very natural field effect transistor or this electrochemical random access memory from IBM. So there are many different choices at the device level. And also recently, I believe the academia and also industry has been working on the macro level demonstration using some of those emerging technologies to build a prototype chip with one array or multiple sub-arrays. For example, here we have some R1 implementations, S1 implementations, even at the leading edge node by TSMC. So here, most of the macros here are designed for only one layer of the network. And therefore here still we are missing the system level multi-macro performance projection from those prototype chips, especially with new emerging technologies. There is a critical need to develop a system level simulator to project the performance and then some design trade-offs if we implement a large scale system using the emerging technologies and circuit design techniques. So here, this is the motivation of our NeuroSim project. So here, this is essentially an open source simulator for computing memory, and this is a GitHub link for the simulator. So this is publicly available, and people can download or clone in the GitHub for their own repository here. So here we have multiple versions. I will discuss that in more details later. And this is a brief history of the project. The first appearance of this NeuroSim simulator was actually back in 2015 in this HANA workshop co-located with CAD. And then we started the integration of this NeuroSim, essentially the circuit level simulator with the neural network model. And the initial integration was the MLP multi-layer perceptron, a very simple two-layer fully connected neural network. And this was published at EDM 17. And later we realized that we need to scale up the problem size and we need to arbitrarily define the neural network model. Therefore, we decided to have this integration with PyTorch, a popular machine learning package. So we have this DNN plus NeuroSim version. And then the first version published in IEDM 19 was for the inference. And recently we extended the framework to the on-chip training. And this was recently published in TCAD 20. So I would acknowledge the students who contribute to this project as listed here. And recently we did some statistics of the NeuroSim, and currently we have more than 300 users. Recently more than 400 users. Mostly come from the university, but some of them are from the industry and research institute as well, resulting more than 100 publications. And some of the industry researchers who have used the NeuroSim are listed here. And actually we supported some of the researchers to industry researchers to deploy the NeuroSim in their internal research. And some publications resulted from different institutions and appeared in different conferences or journals. So let me dive into the technical details. First of all, methodology framework. So this aims to have an end-to-end benchmarking, and first the inference, and then online training, and then we will briefly talk about the 3D integration. So the input parameters for the simulator include the device level parameters and circuit level configuration, and also the architectural level hierarchy and data flow, and then the algorithm and level precision and accuracy in requirements. And then the output from the software hardware co-simulation could report the algorithm level inference and training accuracy under the hardware constraints, for example, the device variation or limited device precision. And then the circuit level performance, energy efficiency, and compute density. So the algorithm accuracy estimation is based on this WAGE method. So basically, we do a hardware-aware quantization for all the parameters in the algorithm, including the weight, activation, gradient, error, and as well as the partial sum quantization, because we use ADC, and ADC may have the limited precision. And we support various network models for CFA10100 and ImageNet, including the VGG, ResNet, BenchNet, and so on. And then the hardware metrics are based on analytic models that are calibrated with space at the module level. We're not running the full system space simulation. That will take forever. So here what we do is to calibrate the module level performance, like the latency, delay, power, and the energy at the module level, like the adder, shift register, or ADC, for example. And then we use analytical models to reconstruct the whole system. So here we provide a massive options at the device level, technology level. We provide the tech node from 130 nanometer down to 7 nanometer based on the PTM model for the transistor performance. And then the device type, different device options, different like the unsplit resistance, which is identified as one of the critical parameter, and ADC options like the flash ADC, SAR ADC, and so on. So there are many design options. And then the analog modules like ADC are calibrated with space level simulations impedance. And digital modules are estimated with the standard cell library in terms of the cell height, cell width, and the logic gate delay and dynamic power, leakage power based on the analytical equations. And also we account for the interconnect parasitic RC delay and power. So some methodologies for the area estimation. So first we need to look at the device options. For example, if it's non-volatile memory, then whether it's a 1T1R or crossbar with a selector. And then we will calculate the array size depending on the cell layout. And then we will define the peripheral circuits according to the array size to automatically match the pitch of the column. We may have to fold some of the peripheral circuits. And we may have to use marks to share. For example, typically for the non-volatile memory, the column pitch is smaller than the, for example, ADC pitch. Therefore, we may have to share one ADC with multiple columns. And then we will also define the peripheral circuits modules, as I just mentioned, the precision of ADC, ADC mode, ADC marks sharing those parameters. And then the latency estimation. So we will look at whether it's read or write. And then for the read, we will look at the digital blocks and then try to estimate the RC delay depending on the transistor parameters like on-state current and then parasitic capacitance. And then for the analog path, we have to fit with some space simulation because it's hard to analytically model that. We will do some simulation and to fit the real traces depending on the input current to the ADC, for example, to figure out the ADC delay. And then we consider the operations. For example, sometimes we can pipeline the operation or we can hide some of the latency if we do two operations in parallel. So we're going to look at the operation scheme and then determine the final latency for some critical operations. We need to find the critical path. And then dynamic energy estimation. So we will do the CV square for the digital operations and consider the array parasitics as well, especially the parasitic RC, parasitic C. And then we're going to sum up all the CV square for the digital operations. And then for the analog operation, if you have some DC paths from VDD to ground, then we have to consider for the static energy. So we need to do some space level simulations again to calibrate that. So here are some overall flow of the version 1 for the inference engine. So here we can define arbitrary neural network in the PyTorch, and this is in Python environment. And then we need to incorporate the device level or the circuit level non-ideal effects into the accuracy estimation. For example, here, if the weight, let's say if the device retention has some problem, so the conductance drift over time, then that may impact the inference accuracy. Accuracy may also drift over time. So we need to incorporate those non-ideal behaviors into the algorithm to check the inference accuracy. And also the ADC may have the limited precision to quantize the partial sum. Therefore, the ADC precision may also impact the inference accuracy. And also the ADC offset due to the process variation may also impact the accuracy. So basically the simulator can handle all of those non-ideal effects at the device level and the circuit level, and then we can report the inference accuracy under those hardware non-ideal effects. And then this is done in the Python for the accuracy. And then we need to do the circuit level performance projection. So here this is done in the NeuroSim core, which is based on C++. And we need to take the traces from the neural network. So here the simulator will automatically plan the chip floor plan and into different tiles. And then we need to unroll the synaptic weights and neural activations into vectors and matrices. And then we need to do the real trace-based estimation on the energy latency, and depending on the real workloads. So here we have hierarchical design and into the chip level, tile level, PE level, and the synaptic array level. I will elaborate more in the next slide. So here are more, this is a closer look. So basically at the level, we have multiple tile and we have the global buffer and then the neural activation and functions, mostly in digital circuits. And then we need to break down one tile into multiple PEs and with the PE level input and output buffer. And here we do have the adder tree for the partial sum accumulation. And then one PE may be break down into multiple synaptic array. And then we have the array level input and output buffer and so on. So if you look into one array, then you can have different design options. We support the SRAM as a baseline. And then the two terminal number tile memory, like 1T1R, can be R1 or constraint memory or other memories, as long as you can represent it as a resistor. And then three terminal devices, for example, here we can have the FE-FET, or you can have the low flash if you wish. So basically we have three terminal configurations for the synaptic array. So we do include all the peripheral circuits to support the compute mode in parallel. And here just some system level benchmark for ADC precision impact as a function of array size. I will skip the details, but basically you can do a sweep of the array size of the ADC precision, and then you can look at the trade-offs in terms of accuracy, area efficiency, throughput, energy efficiency, and so on. And here, the ADC precision will also impact the inference accuracy. So for a reasonably sized array, you have to maintain the ADC at least 5 bits for the partial sum. And also ADC may have different design options. So there are two popular ADCs. One is flash ADC, one is the SAR ADC. So basically flash ADC have multiple comparators. You can do the ADC conversion in one cycle. But for the SAR ADC, you have to trade off between the area and the latency. You have to do multiple cycles depending on the data. Here, you have to dynamically change the references. So here are some comparisons between the SAR ADC and flash ADC. So the basic conclusion is that for the partial sum precision, like 3-bit or 4-bit, basically no precision, the flash ADC can provide a fast conversion and a reasonably sized area and power. But for higher precision, like 5-bit or above, SAR ADC needs to be used because the flash ADC, the energy and the area overhead will exponentially increase. And a few more words on the weight mapping and duplication strategies. So because we support the convolutional neural network, we have to unroll the convolution kernels into the memory array. So essentially, you have a three-dimensional tensor or four-dimensional tensor, including multiple channels. Then you have to unroll the tensors into a two-dimensional matrix. So there are different mapping schemes. So here first, this is conventional mapping. What you can do is to, for example, the input feature map is a cube, but you can look at the kernel size, for example, 3 by 3 by 128. Then you can unroll this kernel into a very long vector, like a 3 by 3 9, and then 128. So roughly 1,000. So you have 1,000 elements in one column, and then also similarly unroll the corresponding window in the input feature map into a long vector, and then you do the element-wise multiplication and do the accumulation vertically. So this is to generate one output vector for the output feature map. So you have to do it in many cycles as the window scan over the input feature map. And also you may need to partition the array because this could be 1,000 by 1,000 if you unroll into a matrix. So the memory array size typically be 128 or 256. Then you may have to partition the array. But this one, the input reuse is low, efficiency is low. So we propose a novel mapping. So here we are going to use multiple subarrays. So each subarray will be corresponding to one entry of this kernel. So for example, 3 by 3 kernel, then we have 9 subarrays. Then we can just use one subarray to deal with one entry of this kernel. Then we can reuse many of the inputs without reloading from the global buffer. And then we can do the partial sum accumulation using the additional digital circuit. So here is, I will skip the details, but this is a data flow if we use a novel mapping. So we can borrow some ideas of the systolic array because the input feature map could be shifted to the neighboring subarray in the next cycle. So we can reduce the long distance data transfer in the local processing. And also we need to somehow consider the weight duplication, especially in the shallow layers, because the input feature map is huge, but the kernel size, even you unroll it, then it's relatively small. So we need to duplicate the kernels into multiple arrays. Therefore, we can speed up the convolution, especially for the shallow layers. So those considerations could be specified in the simulator, like the duplication factor. So with those design considerations, so here we show some of the benchmark results using a VGG8 network for CIFAR10 as an example. So here we try to benchmark at different technology nodes because SRAM is available at leading edge node and non-volatile memories. Today, at most, we can do at 22 nanometer from the industry. So here we get the key parameters from the papers. And then, for example, on-state resistance is identified to be one of the key device parameters because that will directly affect the energy efficiency of the inference. So we need to have the on-state resistance larger than 100 kilo ohm to get a reasonable energy efficiency for 8-bit by 8-bit operation. And for example, here, if the on-state is only 6 kilo ohm, the energy efficiency is not that great, even less than the SRAM at leading edge load. So here are the key metrics on the resistance about 100 kilo ohm to 1 mega ohm. If it's too large, then the latency will be sacrificed. So this is a sweet spot for the on-state resistance of the technology. And also we should try to have multi-level states if you want to compete with the 7 nanometer SRAM in terms of the area, because the non-volatile memory these days is at the older technology node. And one benefit we identify for the non-volatile memory is that for the edge settings, So the compute versus the standby ratio could be low. So let's say activity factor is low. So in most of the time, the device is in the standby or the sleep mode. So if that is the case, then the number-time memory here, most of them, you see that at the 0.1, like 10% activity ratio, they can outperform the 7nm SRAM, which is a black curve here in terms of energy efficiency. So this is because we can power off the unused memory array for the standby mode. And in the number-time memory settings, we can save the leakage power. And a few more words on the version 2. This is for online training. So to support the training on chip, so we have to evaluate some of the weight update strategies and also the non-ideal effects associated with the devices for the weight update. So in the data flow here, basically we need to address the backpropagation. And in the backpropagation, so we have some non-ideal weight update behaviors from the devices. I will discuss that in the next few slides. And also for the circuit level simulation, I believe that for the training version, we need to add the gradient calculation module. So basically in the training, you have feed-forward, backward propagation. So after the backward propagation, then we need to do the gradient calculation between the arrow and the input activation. So there's another convolution between the arrow and the activation. We need to have additional circuit to do that. And this is what I just mentioned. So we need to have an additional module like this weight gradient calculation. And you can also use the computing memory for that weight gradient calculation, but you have to definitely write the data on this module because the arrow and the activation both are dynamic. So those will be changed frequently as you go through the batches. This is unlike the inference. The weight is stationary, right? So the weight is pre-trained, so we don't need to change that. So in this case, we have to use SRAM because SRAM write is efficient. So some challenges in the weight update if we directly do the training on the device. So the device conductance modulation may follow this blue and red trajectory. So the weight increase or conductance increase may follow the blue one and decrease may follow the red one. So this creates the asymmetry and the nonlinearity problem. So here from our analysis, we see that if you have this asymmetry and nonlinearity, then the training accuracy will be degrading very rapidly. And one of the challenges is that because you have the nonlinearity and asymmetry, so most of the weights will concentrate in the middle. Because, for example, if you keep doing the weight increase by the gradient, but somehow in the next cycle, if you have a negative gradient, then you will jump back to the middle of the conductance range. So this stand flip accidentally will cause the distribution of the weight to be concentrated in the middle. This will prevent the circuit to, prevent the network to converge in its optimal configuration. Therefore, the training accuracy is low. So here, one strategy to mitigate that is to introduce the momentum in the weight update. So basically, the weight update does not only depend on the current gradients, but also depend on the gradients in the previous few steps. So if you do that, so here you see that with the momentum, then even under some severe nonlinearity, then the training accuracy can be somehow recovered. But still, as you see that the training accuracy is somehow affected by the nonlinearity. So besides the nonlinearity, there could be device-to-device variation or cycle-to-cycle variation. So the training curve will deviate from its ideal curve. So here we'll also evaluate that. So I'll skip the traces here. So basically, the conclusion is that under the device-to-device variation, then the training can still converge in most cases, and then the degradation could be somehow tolerated by the neural network resilience by itself. But the cycle-to-cycle variation, if it's small, then it's okay, but if the cycle vibration is too significant, then the training accuracy will be degraded because it's more like a random update instead of the deterministic update predicted by the gradient. And then the online training system performance, I will skip the details, but here the key conclusion is that no matter which on-chip technology you use, the bottleneck for the training is the off-chip DRAM access. Because even for a 10 megabyte model, for example, your ResNet 18, you have only 10 megabytes for the weight. But during the training stage, you will generate like more than gigabyte intermediate data for the activation and errors. So there's no way to store the gigabyte model, a gigabyte intermediate data on chip. So you have to save those on off-chip DRAM. So once you go off-chip, then all the energy spent on the DRAM interface. So that's why here you see the benchmark table. I'll skip the details, but you see the overall energy efficiency, training energy efficiency is around 2 TOPS per watt, no matter what technology you use for the on-chip. So this is a big challenge for the training. So that's why I said that I do not believe training from scratch is an appropriate way to go for the computing memory, unless we can address the DRAM interface issue. So I'll skip this one, since I do not believe this is very promising for the training. And next few slides, I want to show some recent updates with the NeuroSim framework. First one is that we validate the prediction from the NeuroSim with the real chip that we designed, also by our group. So thanks to TSMC's collaboration, we designed and taped out a chip at TSMC 40 nanometer with the RM technology. And since we designed the chip, we have a full control. Therefore, we can break down each module and then calibrate the prediction from NeuroSim versus the chip level, or either the post-layout simulation or measurement results. So basically, we need to add some adjustment factors to the NeuroSim prediction to compensate some of the errors. So those adjustment factors will calibrate the transistor sizing effect, the wiring area in the real layout. For example, the marks, we have a lot of routing needed for the wires, which could not be directly modeled by the NeuroSim, and also the gate switching activity and post-layout performance drop. So once we add some of those coefficients, then we can achieve less than 2% errors in between the NeuroSim and the real chip implementation. So here is a roadmap for the NeuroSim extension. So I will briefly talk about one by one, maybe one slide each. So here, the first one is to have it reconfigurable, because the initial NeuroSim will just design one chip, customized to one neural network model. But we have to support different models on the same chip. So it's like FPGA, you have to reconfigure a little bit. We need to add some modules for that. And second one is that we believe that the future is all about 3D integration. And we support the modernistic 3D and heterogeneous 3D. And then recently, we also became interested in the cryogenic operations to design the accelerators, especially for the data center at the lower temperature to boost the performance. And finally, we believe the only way to address the large model and gigabyte model problem is to do the 3D NAND implementation, because that's only high density memory we can use for the computing memory. So I will give one short introduction about each of those extensions. So the first one, reconfigurable design. So basically, we need to define the strategies if the, let's say, the neural network model and the on-chip resources do not match. For example, number of PEs do not match. Then we have to use multiple PEs and then do some reconstruction and to basically reconstruct the partial sum from the unmatched on-chip resources and the neural network model. So we need to add some reconfigurable router to the output of the each P. I'll skip the details, but this has been done already. And then second one is the modernistic 3D. So we need to use back-end line transistor technology to build the active transistors on the back end, on the interconnect level. So therefore, we can partition the design into 2 tiers. So we also need to take care of the thermal dissipation issues. We need to model the temperature of the entire chip if we do multiple tiers. So if we can do that, for example, we can use some advanced technology nodes to build the digital circuit on the bottom substrate, and then we use some legacy node to design the memories on top. So this could utilize the advantages of both advanced digital CMOS and also the non-volatile memories on the back end. And heterogeneous 3D. So this is like the TSV and the hybrid bonding. So this is the only way to do a really large scale system. If we want to map on your ultra large model, then we have to do the stacking and bonding. So here we supported the heterogeneous 3D and the TSV parameters. Let's skip the details. And cryogenic, we need to refit the transistor model at lower temperature and then redesign the threshold voltage for the low temperature operations. Therefore, we can find the optimal VDD. So basically, we can lower the VDD at lower temperature. Therefore, we can save the energy and power. And here, this is for the 3D NAND-based design. And this is the only way to do the gigabyte or terabyte model, because you know the computer vision model, like the ResNet, is pretty small, like tens of megabytes. But if you look at the language translation model, the NLP or the recommendation system, then it could be easily like gigabyte or hundreds gigabytes to terabytes. So the only way to do that is to do it in 3D NAND. So we have to change some of the peripheral circuits to support the computing memory in 3D NAND as well. And we have pioneered in this direction. And I'll skip the details, but I believe this is the only way to go for the gigabyte model. So how much time do I have here? So I have some tutorials for how to run the code, but I think I can skip that, or should I just?
Yeah, I think you have a few minutes. I think, yeah, let's say 10 minutes. Is that good?
Okay, let me quickly go over the examples running the code. So if you run the NeuroSim, so you can define some of the parameters at device level in the parameters.cpp file. So basically here you can define the memory type, like SRAM or 2-terminal device or 3-terminal device. And then you can define the precision of the memory cell. And then for different technologies, you may define their own attributes, like the cell size, the write voltage, read voltage, the on-state resistance, off-state resistance, and so on. And then you need to define the peripheral circuits technology node from 130 nanometer down to 7. And then subarray size, 128 by 128 or 256 by 256. And then ADC type, like SAR ADC, flash ADC, and the current sharing. So then those are the circuit level parameters. And then on the algorithm level, then you can load in some pre-trained model, or you can define your own neural network model. And then you can define the resolution, for example, all 8 bits for the model, or you can even do lower precision. And then we can include the partial sum quantization effect and non-ideal effects, like retention, variation, and so on. So if you turn on those options, you may see the accuracy degradation. And then here are some flow. If you self-define the network model, then you have to train your network first, and then compile it, and then load in to the NeuroSim. So for example, you have to create your own model by defining the network structure, like the input feature map, kernel size, and so on. And then the output, so this is the overall flow. So you define those parameters and compile your files. And then this is optional. If you want to train your own model, then you have to run the PyTorch again. And then this is an output example. So for example, here, this is the training accuracy, the inference accuracy, 90%. And then it will tell you the configuration of the here, each tile support which layer, and then the duplication utilization ratio of each layer. And then it will tell you the performance breakdown. And so for the different components, like the buffer, interconnect, ADC accumulation in terms of latency and energy breakdown. And eventually, it will give you a summary at the system level, including the clock frequency and the total chip area, latency, energy, and so on. And eventually, it will help you to calculate the energy efficiency, depending on you are doing layer by layer or pipeline. So in this case, 24 TOPS per watt. So it will generate all the metrics at the system level. With this, I have to thank all the students contribute to the project and the sponsors of the project, including NSF, SRC, especially the JUMP program, and we are part of the Ascent Center. And with this, I'd like to stop, and I'm happy to have further discussions.
Excellent. Thank you very much, Shimeng, for the presentation. Let me stop the recording first.